section 3.2, and we're getting into some more specific work with derivatives in this section. So up till now we've looked at the derivative as being the approximate value between 2 points, and we're going to call them x and c here, where we do something like this, and there's my x value, there's c, and I take the slope, or the approximate value, also called the difference quotient or the average rate of change from x to c. So we're taking an average rate of change here, and as you know, we want to get towards our exact rate of change. You've also seen this in your pre-cal textbook where they call it f of x plus h minus f of x over h. The only difference here is that instead of labeling this x and c, we label it x and x plus h, where the distance between these two was h units, and that was our slope again between those two values. Now both of these are approximations. What we want to do is we want to bring c closer to x, or x closer to c, let's say as x approaches c. If we bring this value this way, and these 2 points get closer and closer to each other, or if we make h approximate 0, in other words, bringing the value this way, so that we can again get a tangent line almost, or a secant line that is so small that this slope between 2 points begins to approximate the actual derivative. Well, we're going to learn to do that algebraically and find the exact derivative, or the instantaneous rate of change. We've changed one thing here in our definition. Now we're saying, and this is read f prime of c, f prime of c, which is the derivative, equals exactly the limit as x approaches c of this difference quotient. In other words, I have two values. It really doesn't matter which side I make c and which side I make x. But as x approaches c, if I take the limit of all of these values as we are getting closer and closer as x is approaching c, then if I take the limit of those values, I will eventually get the value when x is c. Again, algebraically, we cannot find a slope at one point, so if x equals c, we can't do this slope. We get 0 over 0. But if we take the limit of all these values as x approaches c, then we can get the instantaneous rate of change. So algebraically, if f of x is a function, x squared minus 3x minus 4, and I want to find f prime of 5, I am going to say f prime of 5 equals the limit as x approaches 5 of f of x minus f of 5 over x minus 5. Shut off the video for a moment and substitute f of x into this place, find the value of x of 5, and get a new quotient for me. Okay, whoops. We should have found that f prime of 5 is now equal to the limit as x approaches 5 of x squared minus 3x minus 4 minus, when I plug in f of 5, I get 25 minus 15 minus 4, and that equals 6 over x minus 5. Simplifying, we take the limit as x approaches 5 of x squared minus 3x minus 10 over x minus 5. It's absolutely critical that you continue to write that we are looking for the limit as x approaches 5. Notice that we cannot plug in x equals 5. If I plug in x equals 5 right now, I get 0 over 0. So I'm not looking for this value, I'm looking for the limit of the value as we make x really, really close to 5. So I could plug in 4.99 or 5.001 and get a table of values for this difference quotient, so that as we approach 5, which is undefined or indeterminate, then I will find that I am approaching a certain value. However, I'd like to be able to do this algebraically without having to plug in values close to 5. I'd actually like to find out what happens at 5. Well, if I continue with my work, and if I factor the numerator and simplify, we will see that the limit of my difference quotient as x approaches 5 of x plus 2 will actually equal 7. Now remember, this statement that these two are equal is true only when x does not equal 5, and yet I'm plugging 5 in. Again, this is because the limit doesn't care what happens at 5, only what happens really, really close. So therefore, the limit of my original difference quotient will equal the limit of my simplified value, and now I'm to a place where I can actually plug 5 into the equation, and we find that the limit is 5. Therefore, f prime of 5 equals 7. We have just found the slope of the tangent line to this curve, which is a parabola, at the exact place where x equals 5. Take a look at this example again until you're sure that you understand. And if you have questions, bring them to class. The graphical definition is that the derivative of a function at a point equals the slope of the tangent line to the graph. So both the derivative and the slope of the tangent line equal the instantaneous rate of change. Please write that down as well. So we have two definitions. One is our f prime of x, or f prime of c, if we're looking for a specific value of c, equals f of x. Excuse me, I almost messed that up. F prime of c is the limit as x approaches c of f of x minus f of c over x minus c. That's the derivative algebraically. The derivative graphically is the slope of the tangent line. Those are the two definitions for 3.2. And that's it.